Yes friends, welcome once again to the class. So we will learn about isobaric nuclei with E1A. Okay. Now for nuclei which have even atomic mass number A, the nuclei for which the mass number A is even, for them two cases might arise. Okay. That the number of protons is also even, number of neutron is also even, then also even plus even is equal to odd, or else the number of proton is also odd and number of neutron is also odd. So in that case also the atomic mass number A will be even only. Okay. So isobaric nuclei with even A means two situations will arise, that Z is equal to even and number of proton equal to even, number of neutron equal to even, then also even plus even equal to even, number of proton equal to odd, number of neutron equal to odd, then also odd plus odd equal to even. Okay. So isobaric nuclei with even A. Okay. So MZA, this is your isotopic mass of the nuclei. Okay. So this is the isobaric this is isotopic mass which is there, isotopic mass of the isobar having atomic mass number A. So the isotopic mass is given like this, which we have derived in the previous lectures. This expression we have already derived in previous class. K1A plus K2Z plus K3Z square plus minus delta. Okay, we have already derived in the previous classes. Now for nuclei which have even atomic mass number A, what happens is that delta, which is the, I think it is pairing energy, right? So delta is positive for even nuclei, and delta is negative for odd nuclei. Okay. So thus masses of isobars, the masses of isobars. So the masses of isobars, as the delta is positive, pairing energy is positive. So the mass will be negative, because the corresponding to this being positive, the term here is negative, and corresponding to this being negative, the term here is positive. Okay. So pairing energy is added, pairing energy is subtracted when it is positive, and when it is negative it is added. Okay, it is other way around. So the masses of E nuclei will be lower than the masses of O nuclei. Okay, and as the masses of E nuclei will be lesser than the masses of O nuclei, so what will happen? The parabola of E nuclei will lie in the lower region, in the lower region, and odd nuclei parabola will lie in the upper region. So the masses of isobar fall on a separate lower parabola than that of the O isobar. So masses of isobars fall on a separate lower parabola than that for the O isobars. Okay. We have we have equation 5 from previous lecture. You can also see over here that this is for the EE nuclei. This parabola is for the EE nuclei. Okay. So the mass, isotopic mass is lower. Okay. As compared to this, the masses are lower. So as the masses will be lower, so mass defect will be higher. Masses will be lower, so mass defect will be higher, and as mass defect will be higher, greater will be the energy released during formation of such a nucleus. So more stable is such a nucleus. So these nuclei are more stable. EE nuclei are more stable, and O nuclei are less stable. Okay. From equation 5 from previous lecture, which we had derived in the previous class, you must have seen the previous class. So from equation 5 which we have derived in the previous class, that is mzs comma A, ZS means Z most stable. ZS means this region. Okay, this is the line of ZS. Okay, around this region somewhere ZS will lie. Around this region somewhere the Z most stable will lie. Okay, because the mass is lowest at that point. It is the minima of the parabola. So from equation 5, in the previous lecture we have something of this kind which we had derived in the previous class. Writing equation 5 for E1A. Now if we write this for E1A but OO nuclei. Let us write this for OO nuclei. Then OO nuclei has higher mass, so mass defect is lower. Okay, it has higher mass, so this delta will be added in it. In this expression, for odd nuclei, delta will be added. For E1A only, A will be even in both the cases, but instead of OO, now we have EE nucleus. For instead of OO, we have EE nucleus. Then what will happen? The same expression, as the EE nuclei are more stable, so mass must be reduced. So we have subtracted delta from this. Okay. So this is your equation number 9. This is your equation number 8. Thus the vertical separation between the two parabolas, how will it be given? Vertical separation between the two parabolas will be given by the subtraction of this. Okay, vertical separation between the two parabolas will be given like this, right? And it will be 2 delta everywhere. Over here also, if we draw a vertical line, suppose we draw a vertical line like this over here, suppose. Okay, then the difference, this is suppose vertical. Okay, so the difference between these two will also be 2 delta only. Okay, this distance will also be 2 delta only. It will not be different. It is going to remain constant. Vertical separation is going to remain constant everywhere. Although in the figure it is not looking like that, but it is going to remain the same everywhere. This will also be 2 delta. Okay. Similarly, if you draw over here also, that is the same thing, that this will be in fact 2 delta. Okay, so this is the thing. Thus the vertical separation between the two parabolas is m odd for odd the mass is there, and for even the mass is there. We will subtract from odd the even mass. Okay, A will be, atomic mass number will be even in both the cases, but the number of protons and number of neutrons will be odd over here, and the number of protons and number of neutrons will be even over here. So when we subtract these two, we basically take the difference of these two. Okay, so what do you get? 2 delta you get. Let this be equation number 10. Okay, the behavior of isobars in beta decay for odd A isobars. Okay, for now this parabola I have already discussed to you. Parabola I have already discussed to you. How I have discussed? See, these are two quadratic equations, right? This will represent OO. So equation 8 represents OO. Equation 9 represents EE. So equation 9 has been plotted over here. This is your equation number 9 plotted. Okay, over here equation 9 has been plotted. Okay, and over here equation 8 has been plotted on the upside. Downward side equation 9 has been plotted. This is equation 9, and upper side this equation 9 has been plotted on the downward side of the curve. Two parabolas we have got, right? And this has been plotted in the upper part. Okay, so that's how you can see this. Behavior of isobars in beta decay for odd A isobars. Okay, now we are talking about atomic mass number A to be odd. Okay, For odd A isobars, all isobars whose binding energies are less than that of the stable one will lie on the two arms of the curve. Okay. Suppose we have odd A, means the atomic mass number A is odd for some isobar. Suppose then all those isobars whose binding energies are less than that of the stable one. Okay, binding energy less than that of the stable one means suppose we have a situation of this kind. You only look at this. Okay, we had drawn the odd graph in the previous not A equal to atomic mass number A equal to odd graph we have already drawn. We, instead of getting two parabolas, you get a single parabola in case of odd A. In case of odd A, in case of even A, you get two parabolas, but in case of odd A, you will get only one parabola. So we had already discussed this in the previous lecture. So for odd A isobars, what is it saying? What is it saying? For odd A isobars, all isobars whose binding energies are less than that of stable one will lie on the two arms of the curve. Okay. For odd A, okay, odd A means all isobars whose binding energies are less than this. This is the most stable binding energy. This one is the most stable binding energy because mass is least on either side of the curve. When you move on either side of the curve from this mean position, which is ZS position, the mass increases. The mass increases on either side. The mass increases on either side. Okay, because when you draw the horizontal from here, you will get higher value of mza, because this is what? This is your mza. Okay, this is your mz comma a. Okay, this is your mz comma a. So that's why. So for odd A isobars, all isobars whose binding energies are less than that of the stable one. Lesser binding energy means more mass. Lesser binding energy means more mass. Okay, will lie on two arms of the curve. All these isobars decay into stable isobars. So all these isobars, let's look at the figure. All these isobars, this is the ZS. Okay, all these isobars, those who have the same atomic mass number A, which is equal to odd, all these isobars decay finally into some nucleus nearby ZS. So over here in real life, Cu65 is the nearest. In real life, Cu65 is the nearest naturally occurring nuclei, which is nearest to this ZS. Okay, and has the least mass. Least mass means most binding energy. Least mass means most mass defect. Least mass means more mass defect. Now more mass defect implies that higher is the binding energy. Okay, so this particular point will imply that it has the least mass. So it is not necessary in real life that always ZS will lie at the exact minima. It's not necessary, because the minima might be at decimal point also. The minima might exist at decimal point also, but a naturally occurring nuclei will have Z always integer, never fractional. So if suppose this ZS is fractional, so nearest integer will be the your ZS. Okay, real life ZS. This is theoretical ZS, which has been obtained by finding the minima of the graph, and this is the real life ZS. Okay, so this has the minimum mass. So what every nuclei will do is that every nuclei will decay into this. Okay, every nuclei will decay into this. Every nuclei on the right hand side will decay into this. Will try to decay into this ZS. Okay, all those isobars decay into stable isobars either by beta minus emission, where Z is smaller than ZS, or by beta positive emission, Z is greater than ZS. Now the situation is something like this. Okay, you have ZS over here, and the atomic number of copper is 29. Atomic mass is 65, but atomic number is 29. Okay, so why they are decaying, why they are undergoing beta minus decay, and why they are undergoing beta plus decay, we will understand now. suppose iron, cobalt, nickel, copper, zinc. Okay, so what you have is that iron, cobalt, iron is I think 26, cobalt, nickel will be 28. Okay, nickel, copper, and then we have zinc which is equal to 30, then gallium which is equal to 31 atomic mass, not atomic mass, atomic number. Okay, z equal to, and we have germanium equal to 32. Okay, so such is the situation with us. What happens is that suppose in this particular situation the nuclear configuration is such, that for 65 neutrons the nucleus has most stable nuclear configuration. Nucleus has most stable nuclear configuration when 65 atomic mass number corresponds to 29 protons. Okay, when 65 atomic mass number corresponds to 29 protons, only then it is the most stable nuclear configuration, suppose. Okay, when 65 atomic mass number corresponds to 29 protons, means 29 atomic number, then such a situation is suppose most stable nuclear configuration. So clearly those which lie on the left hand side of this curve, left hand side of this copper, like nickel and cobalt. Okay, those have insufficient protons. These have insufficient protons. The over here protons are 27, required is 29. Over here protons are 28, required is 29. Okay, so they will undergo beta minus decay. And what happens in beta minus decay, you know this very well, that in beta minus decay the atomic number increases by 1 unit. So one times cobalt 27 will undergo beta minus decay one time, so it will convert into nickel which has atomic number 28, and then nickel will undergo beta minus decay again, so it will become copper which has atomic number 29. Now it has gained stability. Okay, because 65 mass number corresponds to 29 atomic number, which is the most stable nuclear configuration. Okay, now if we look at the right hand side things, what happens is that on the right hand side we have excess of protons. Okay, so 65 atomic mass number required 29 protons. 65 mass number required 29 protons for maximum stability, but over here instead of 29 protons we have 30 protons, 31 protons, and 32 protons. Okay, so what they undergo is that they undergo beta plus decay, and as soon as they undergo one beta, when they emit one positron, what happens is their atomic number decreases by 1. Okay, so germanium emits one positron, its atomic number decreases by 1 and becomes 31. Again it emits one positron, its atomic number decreases by 1 and it becomes 30. Again it emits a positron, its atomic number decreases by 1 and it becomes 29. Okay, so such is the situation. Okay, so the nuclei which lie to the right hand side of this curve, on the RHS of this curve, they undergo positron decay, and which lie on the left hand side of this curve undergo beta negative decay. Okay, so that has been written over here. All these isobars decay into stable isobars either by beta negative emission, that is your Z is less than Zs. Okay, Z is less than Zs means the left hand side area, and by beta positive emission. Beta positive emission means Z is greater than Zs. Okay, that is the right hand side of the curve. Okay, I have already explained this. So now example is this. This is very clear from the graph. You can see this: cobalt converted to nickel, then converted to copper. The isobars which lie to the right hand side of the lowest point contain an excess of protons, decay by beta positron, beta plus emission. Okay, I already told you. and which lie on the these lie on the right hand side. Okay, right hand side undergo positron, means right hand side ones undergo positron emission and left hand side undergo beta minus emission. So I have already explained all of this to you, so you can simply copy down the slides and understand them. Okay, everything has been explained to you already, so hopefully you got everything. Okay, so thank you very much. If you haven't subscribed to our channel, then please do subscribe to it. Okay, so you must have got the meaning of all these things, hopefully. Okay, so thank you very much. Jai Hind, Jai Bharat.